Hello Summer Institute students, this is the second video in Work and Energy. So here you want to shift over to the notes page that I gave you on the Google Classroom. We'll start with the definition of energy. And again, I'm sure you've encountered energy in a previous science course, and if I asked you to give me a definition for energy, more than likely, with just a little bit of thought, you tell me it is the ability to do work. Which is a little bit odd because on the previous video we just defined work as an exchange of energy. They're kind of flip sides of the same coin. If an object has energy, what can it do? Well, it can do work. When it does work on another object, what does it do? It actually gives its energy to the other object, which means the other object has energy. So what can it do? It can do work. And then it can do work on something else, giving it its energy. And so it's a constant exchange back and forth between work and energy. In energy, we have different categories. And so one category is called mechanical energy. And we define mechanical energy as the sum of Ke, which stands for kinetic energy, and all types of Pe, which stands for potential energy. And I'm sure you've encountered these different types of energy before. You probably have a sense of them. And so on this worksheet, we're just going to go through the definitions and obviously expand your knowledge to the physics level. Our symbol for mechanical energy is going to be E total, since it is the sum of kinetic and potential energies. And so here we have our chart. Let's talk about kinetic energy first. And so if I ask you what kinetic energy is the energy of, I'm sure you'd all tell me, of course, it's energy of motion, right? Objects that are moving have a kinetic form of energy. What does it depend on? Well, you've probably done some problems before in previous science courses, maybe you've done some experiments. Imagine an object that's moving. Imagine that object, maybe like a car, is going to run into something and do some work on it. Maybe they're testing out the crash safety of a car. It's going to run into the barrier, right? And so you should imagine that the faster it's moving, the more work it could do on the barrier would move more. So obviously it depends on how fast it's moving, the speed. You also might imagine that if the car is full of the crash test dummies, that has more mass to it, it would plow into the barrier and be able to do more work on it. So it also depends on the mass. And so the more mass an object has, the more kinetic energy it has. If it's moving, the faster it's moving, the more kinetic energy it has. So it depends on mass and speed. We're going to get to the equation, and during the school year, I would show you where the equation comes from, but for now I'm just going to give you the equation, and you can see how it depends on mass and speed. So here it is in words: kinetic energy equals half the mass times the speed squared. I never like to just throw an equation at you. I'd much rather show you where it comes from, but once again, we don't have the time right now. During the school year, I would show you by deriving from equations where this equation comes from. But you can see it relates to mass and speed. Our symbol for kinetic energy will be the double letter you see at the top of the column. It's going to be Ke. So in symbols, this is Ke equals 1/2 mv squared. So you can write that down and box it in as a new equation. It is a scalar quantity. Notice it is speed, not velocity. And so it does not matter in what direction the object moves. As long as the object is moving, it has kinetic energy. So it is a scalar quantity. For the units, well, it comes directly from the equation. Mass is given in kilograms, so there's kilograms. And speed, of course, is in meters per second. We're going to square that, so it's just meters squared per second squared. And so the units for kinetic energy are kilograms meters squared per second squared. Now, this is a rather unwieldy unit. Kilogram meter squared per second squared is difficult to remember, and kilogram meter squared per second squared is difficult to write, and kilograms meter squared per second squared is difficult to say. Luckily, we can play with it. We can rearrange it a little bit. So I'm going to take the meters squared and separate it out as meters times meters. Hopefully we'll all agree that's the same thing. And so now you see here kilogram meter per second squared. You should recognize that as saying mass times acceleration. And of course we know mass times acceleration gets sigma F, or force, and force is measured in newtons. And so we can rewrite this as newtons times meters. Now, if you've been paying attention in your notes that you've written about work, you should see that the Newton meter, of course, is the same thing as a joule. And so we'll just use joules as the units for kinetic energy. Really, joules are the units for any energy, which goes back to the definition that work is an exchange of energy. They must be in the same units. You can write kilogram meter squared per second squared, you can write Newton meters, but really joules are the most convenient units we'll use for kinetic energy. Now let's shift over to potential energy. Following the same format, we want to say potential energy is energy of. And you've seen potential energy in various forms before in previous courses. More than likely you've learned as a stored form of energy, but that really doesn't fit the bill in finishing this phrase. That doesn't say energy of. And so you may know, but if not, I'll tell you, it's energy of position. Notice there's a lot more room here, and so there's going to be more to write. So hopefully you haven't written position very, very large. We're going to expand on this potential energy idea to say, really, an object has potential energy when it is in a location or position where it, quote unquote, doesn't want to be. Here I'm leaving the wording very general because there are different forms of potential energy. But I'm putting this phrase, it doesn't want to be, in quotes because we're talking about inanimate objects. They don't really have wants and needs, and yet it's pretty obvious to tell when an object is in a place where it doesn't want to be. So imagine you have a textbook. Maybe the textbook is sitting on your desk. If it's at rest on your desk, everything's fine. But if you just move it a little bit off that desk at the same height above the floor and let go, what's going to happen? Well, clearly the book is going to fall. It's going to go to the floor, and it's going to stop at the floor. That means that when you had the book at the height of the desk, it didn't really want to be there. You know this because when you let go, it goes somewhere else. And so that's what I mean by doesn't want to be. When you lift the book against gravity and put it at the height of the desk above the floor, it doesn't want to be there. You've stored some energy in it. We call this potential energy. If you were to put something underneath the book, maybe like a plastic cup, and were to drop the book on it, well, then the book would fall on the cup and do some work on it, applying a force through a displacement, which means that the book has some sort of energy. It needs energy to do work on the cup. But again, anywhere you put it where it doesn't want to be, you're storing energy in the system, you're giving it a potential form of energy. Specifically here, we're talking about gravitational potential energy, since you had to lift the book against gravity to get it there. What does the potential energy depend on? Well, I imagine if you were to drop a heavier book, then if you put the cup underneath, it would crush the cup more, which means it depends on the weight of the book. Or, if you were to lift the book to a higher height and drop it against the cup, then certainly you would do more work on the cup. And so we'll say that potential energy, or really gravitational potential energy, depends on height and weight. Once again, I'm going to give you the equation, and during the school year I'll show you where the equation comes from, but here it is. Potential energy equals mass times acceleration due to gravity times height. Or in equation form, we'll use the symbol PE for potential energy. We'll write PE sub G equals mgh, where the subscript G here stands for the gravitational form of potential energy. Now right up here, we said it depends on height and weight, and clearly the height is going to be the h in the equation. Where's the weight? Well, it's right here. mg, of course, we know is the equation for weight. This really then is weight times height. This, of course, is a scalar quantity, just like kinetic energy, just like weight. And we'll define h as our new symbol for height. Height is measured in meters, of course. And PE sub G we define as gravitational potential energy. Throughout the school year, you're going to learn other forms of potential energy, and they'll just get different subscripts here, telling you what type of potential energy it is. For the units, once again, it's the units based on the equation. We got mass in kilograms. G, we of course know, is in meters per second squared. And height, we now know, is in meters. We put it together, and we get kilograms, meters squared per second squared, putting the two factors of meters together. Now, once again, kilogram meters squared per second squared is rather unwieldy. Luckily, we just went through the whole derivation, and we know this really is the same thing as joules. And so we're going to use joules as our units for potential energy. On the worksheet, there are a couple of practice problems for you to go through, so I'd like you to complete those, practicing using the new equations when you're using kinetic energy, when you're using potential energy, and then in class we'll go over the answers and see what sort of patterns have emerged.